Thanks for attending this talk. My name is Sam, and I'm a second-year PhD student at Harvard University. So today, my talk will be on pitching a new way to think about and evaluate deep recommendation inference. I'll be laying out what the issues are in terms of the algorithms, software, and hardware that we put together in deploying these recommendation systems. Now, whether you know it or not, recommendation is used everywhere in our lives. Every time you go to YouTube's homepage, the first things that you see are video recommendations, personalized just for you. When you log on to Facebook, you're served newsfeed posts recommended to you in real time. And after you buy anything on Amazon, they always tempt you to buy more based on your recommendations. Now, these are just some examples. Recommendation systems are also used by other companies to power their key services. To formalize what recommendation is, we're going to borrow a message from our friends at Amazon. What a recommendation system does is that it takes in you and your item preferences and generates more hopefully relevant item recommendations. So, why should computer architects care? For one, there's great real-world impact. For example, when we take a closer look at Facebook's data centers, we see that over 80% of their AI inference cycles are spent on recommendation-related tasks. And it's a similar story for training as well. On top of this, recommendation systems also pose a unique set of compute challenges. First, compared to the well-studied CNNs and RNNs, recommendation systems occupy a different region of the roofline model. What this means is that these industry-represented recommendation systems stress different compute capabilities. Secondly, the model architectures themselves can vary greatly. This leads to a diversity of bottlenecks that we will explore in this talk. In order to efficiently analyze these bottlenecks, we propose using a cross-stack approach. So let's take a peek at a typical execution stack. First, we have the algorithms. Depending on the application, recommendation algorithms used will vary. Because most industry representative algorithms leverage deep learning, this happens in the form of different model architectures. Next, we have the software. Since these models are deep learning based, the model implementations themselves are often based on popular deep learning frameworks. This, however, leads to implementation differences as the software frameworks are not unified. Lastly, we have the hardware platforms. Leveraging heterogeneous hardware in the form of CPUs, GPUs, and accelerators is essential from both efficiency and infrastructure standpoints. This leads to an important observation that different layers of the execution stack have different bottlenecks. So the key question that we want to answer for this talk is, what are the bottlenecks of each layer and how do they affect one another? First, we want to take a look at what these algorithms actually look like from a model architecture perspective. Next, we want to deploy these models out of the box on different CPUs and GPUs for different use cases to see what the performance trends look like. In order to explain these performance trends, we first look at software-level operator usage. Then, we tackle these performance trends from a hardware microarchitectural standpoint. Okay, so model architectures. Unlike other well-studied DNNs, deep recommendation systems have two types of inputs that require different processing techniques. One, continuous inputs, and examples of these are user age and time of day. These are processed by traditional DNN stacks. Two, we have categorical inputs that are used as indices for embedding tables. You can think of these embedding tables as tables that store information on users and items in the form of embeddings. Operation-wise, the inputs, which are multi-hot encoded vectors, are used to access individual entries within the embedding table. After this, we have some post-processing components. This is often in the form of feature pooling and interaction for the initial processing that gets fed into a final DNN stack. The end result will be a click or buy prediction for most recommendation use cases. What's unique about these models, however, is how configurable they are. All of these components shown on this figure can be configured in different ways. For example, in the red blocks, we have different DNN stacks. If the input data is in the form of a time series, we may want to use RNNs instead. And that's just one example of how we can leverage different types of DNN stacks for efficient processing. 2. The embedding tables can be sized differently along their dimensions. We can have more embedding tables or even larger tables. In production cases, these tables often bloat to the gigabytes range. This leads to a need for specialized memory subsystems. What you need to know here, however, is that based on application requirements, we will get different model configurations that lead to different compute requirements. Now, we know what these models look like. Let's see how they perform. Let's take a look at raw performance trends based on different deployment choices for different use cases. Here's an example of the type of result in this section. For specific recommendation model, multitask wide and deep, this is a recommendation model used by YouTube. We evaluated it on 4 different hardware platforms. So there are 2 server class Intel CPUs, Broadwell and Cascade Lake, and 2 NVIDIA GPUs, 1080 Ti and T4. We evaluate each use case across a wide range of batch sizes. This is important as in production cases, the input batch sizes for these recommendation models can vary based on input traffic. So for here, we see that x-axis is batch size, goes from 1 to 10,000, and y-axis is execution time. We represent this as a speed up relative to execution on the Broadwell machine. So first, we observe that there's relatively lots of acceleration when we deploy multitask wide and deep on GPUs. For larger batch sizes of around 1,000, GPUs provide an order of magnitude higher speed up over the baseline Broadwell CPU. For a smaller batch size of less than 100, we still observe a 2 to 4 times speed up. Whether that's from fewer embedding tables or large, fully connected stacks to output final probability scores, models like multitask wide and deep that rely on fully connected stacks to model user preferences. Next, let's take a look at RM1, and this is one of Facebook's recommendation models for its newsfeed service. In contrast to multitask wide and deep, it doesn't perform as well on GPUs. This has to do with how RM1 relies more on embedding table accesses to model user preference. For example, RM1 has a large number of lookups per embedding table for each input, like around 80 in our evaluation case. In comparison, the other models have fewer than 20 lookups per table. Next, we want to talk about how different model architecture implementations of a high-level idea, like the attention mechanism, can have different system performance implications. Now we look at, these are 2 models used by Alibaba in their services, DIN, the Deep Interest Network, and DIEN, the Deep Interest Evolution Network. Algorithmically, both DIN and DIEN use attention to learn users' evolving interests over time. DIN implements attention with local activation units and concatenation operations. DIEN, on the other hand, implements attention using multi-layered gated recurrent units, GRUs. Since the latter translates better to regular matrix operations, we get better GPU performance for DIEN. Now, to summarize, the key point here is model architecture and use case play an important role in determining acceleration. In summary, optimal hardware varies greatly for these different use cases. In here, I've shown the optimal hardware for each use case with the shading of the blocks and the optimal speedup that comes with this platform with the number within the block. Next, we want to go one step up and try to explain these performance trends from a software operator perspective. And this is important for 2 reasons. One, it's often hard to have a one-to-one comparison with different model architectures since they come in different sizes and shapes. Operator breakdown is a good, unifying, fair approach for comparison. 2, using this approach will expose future optimization opportunities. There are 2 main observations, but let's go over the general structure of these figures. For each model architecture, like multitask wide and deep, We can break down the software execution time by operator usage. For example, in multitask wide and deep, we spend most of our time on fully connected layers, while on RM1, we spend most of our time on embedding operations at larger batch sizes. Now, we blow up these results for all four hardware platforms. The first insight that I have is if a model is bottlenecked by fully connected operations on a CPU, deploying this model on a GPU will give us significantly better performance. We can see this from this operator breakdown by how much the GPU accelerates the fully connected operation. For example, if you look at the right side of this figure, on the GPU operator breakdowns, the red bar, the percentage of the red bar is decreased. The second insight is that if a model spends most of its time doing embedding operations on a CPU, deploying this model on the GPU won't be as effective, since the GPU doesn't accelerate the embedding operation as well. A lot of this has to do with how data communication overheads are a significant factor for GPU deployment, and this is covered in the paper. Lastly, between hardware generations of the same hardware type, we see minor changes in percentages, but dominant operators will still remain dominant in execution time. Lastly, we want to tackle the performance trends from a microarchitectural standpoint. As we all know, modern processors can be split into frontend and backend. Within frontend, we can classify our problems as either latency or bandwidth related, and within backend, we can classify our problems as either core or memory related. At first glance, we've broken down our model execution pipelines into 4 categories: retiring, front-end bound, bad speculation, and back-end bound. Now, there are quite a few takeaways from our microarchitectural analysis, but I want to focus on 3 of them for this talk. First, fully connected heavy models are back-end bound. More specifically, they are core bound by insufficient functional units on Broadwell machines. Now, how do we know this from the plot? First, from here, we see that multitask wide and deep is back-end bound. But within back-end bound, is it core bound or memory bound? The graph on the right shows us the breakdown of all back-end bound cycles as a ratio of core bound cycles to memory bound cycles. This means that if a bar is greater than 1, this means that that particular execution was core bound as opposed to memory bound. And this is exactly the case for multitask wide and deep. If you go further into this analysis, we also see that multitask wide and deep already saturates the amount of functional units available on Broadwell. And this has shown that over half of its cycles, it's already using more than 3 functional units at a time. And this is on a Broadwell machine. Recall that there are 8 functional units. And if you're using more than 3 functional units in a cycle, that's showing good usage. On the flip side, we want to look at how this translates to Cascade Lake. What's interesting is that running multitask wide and deep on Cascade Lake still results in a back-end bound execution. However, in this case, the back-end bound cycles are memory bound. We see that in both of the graphs on the right, when there are more memory bound cycles on top, and functional unit usage is decreased on the bottom. Second, I want to talk about the front-end latency issues for attention-heavy models like DIN and DIEN. Recall that for recommendation systems, attention allows networks to individually weigh the importance of embedding vectors to offer better personalization. In DIN, attention is implemented using hundreds of local concatenation and fully connected layers. This leads to a large number of instructions with unique reference locations, since the instruction cache does not cache opcodes, but specific instructions, including the reference operand. Given unique memory addresses for embedding table lookups, the instruction cache hit rate suffers from irregular memory accesses. And this is another way to explain this is from the lack of spatial and temporal locality. There are some differences here between DIN and DIEN, and a lot of this has to do with the model architecture and how they implement attention. The details are covered in the paper. Third, I want to talk about models that rely on embedding lookups. So recall that for front-end decoder pipelines, the two main decoder microarchitecture components are the DSP, the decoded iCache, and the legacy decoder pipeline, the MITE. So functionality-wise, the DSP acts as a cache for MITE. We first search through the DSP if the cache instruction is there. If it isn't, then we have to fetch and decode the instruction MITE and put the results inside the DSP. Now shown in this graph are the percentage of cycles in which the CPU is limited by a specific decoder component. Basically, we're showing here is the cycles when the specified component was not outputting an optimal number of decoded instructions for the backend to use. Particularly, ARM1 shows issues with its DSP. And this DSP bottleneck can be tied to algorithmic model architecture features of ARM1. In particular, the model requires a high degree of embedding lookups. In summary, different types of model architectures lead to different microarchitectural insights that have performance implications. For fully connected heavy models, when we look at their execution on Broadwell machines, we realize that they're bottlenecked by insufficient functional units. When we deploy the same models on Cascade Lake, we realize that the bottleneck has already shifted to a memory subsystem. What's interesting is that we actually see a similar trend when we deploy these models from CPUs to GPUs, as GPUs offer better functional units in the form of their high streaming multiprocessor counts. Our bottlenecks are shifted to the memory subsystem for the GPU as well. Now, for these attention-heavy models, we're usually front-end latency bound, and we can see this through the L1 instruction miss rates. Decodely, for these embedding heavy models, we're usually front-end bandwidth bound, and we can see these from the decoded iCache. To summarize, we first took a look at what these models look like. Then we examined how they performed at different use cases. In order to explain these performance trends, we looked at them from both the software operator and hardware microarchitecture perspectives to find new optimization opportunities at the software and hardware levels. If there's anything that you need to remember from this talk, it's this. To deploy recommendation efficiently, you have to understand your use case. What application do you plan on running? And what model architecture does that require? And also, at what scale do you expect to run your model at? Second, to improve recommendation, we can find optimized opportunities at both the software and hardware levels. And we can do this by looking at the operator and microarchitectural characterization. If you like this talk, I'd recommend you to take a look at the paper. Within the paper, there are more industry representative models surveyed, more specifically, 8 total models from different companies, and more analysis and insights at both the microarchitectural level and also the operator level. And most importantly, please check out the open source DeepRexis repository. The model implementations and experiment scripts are all published at this GitHub link. I hope you enjoyed this talk. Thanks for listening, and I'd be happy to take any questions.